Yeah. So can you see my screen? Anyone can unmute and tell me?
Yes, sir.
Yeah. Okay. Today the topic we are going to discuss in the fifth unit is P, NP, NP hard, and NP complete problems. Okay. So this may not be new to you because you might have studied this in design and analysis of algorithms. But anyway, I'll be teaching the same thing again. So if you are so confident in your earlier things, I think it's well and good. Okay. So before discussing about this P, NP, NP hard, and NP complete, I hope you might have remembered the notation big O. Okay. So what is this big O notation? Can anyone tell me? Do you remember that? Omega notation, big O notation, theta notation. Okay. So I think most of you might have forgot that, but anyway. So this big O notation is a measure of how quickly an algorithm runs or solves a particular problem. I'll repeat again, big O notation is a measure of how quickly an algorithm solves a problem. Okay. So it is a upper bound of how long the runtime of an algorithm is. Okay. So it does not, it represents the upper bound of how long the algorithm runs. So this P, NP, NP hard and NP complete are classes that any problem would fall under or would be classified as P type of problem. So where this P stands for polynomial problem. Okay, P stands for polynomial problem and NP stands for non-deterministic polynomial. It's not non-polynomial, but it is non-deterministic polynomial problem. So I repeat again, P stands for polynomial problem, NP stands for non-deterministic polynomial problem, and we have the concept of NP hard, where NP hard is nothing but when an algorithm for solving can be translated to solve any NP problem. That is, it is at least as hard as any NP problem is there. And of course, we will be discussing about NP complete problem. So this NP complete actually comes under NP and NP hard classes. Okay. So this NP complete problems can be verified in polynomial time. Uh, for example, okay. So like we can say that NP complete is a subset of NP hard and NP maybe, right? Okay. So we'll be discussing more in detail about each of these classes now. First of all, let's go for the exponential complexity. So probably if you want to compute a Fibonacci series up to some 50 terms, I think it is really tough to do it. Your calculators or your computers may not be in a position to compute the Fibonacci series up to 50. Okay. So here we show the big O complexity or the big O notation, and we know that it is, as I told you, it represents the upper bound of how long the runtime of an algorithm is. So you can see sorry, for various problems, you can see that here there are various types of problems where the first one is O of 1, another one is log n, and n log n, n power 2, 2 power n, and n factorial. So you can see that this n factorial and all you cannot compute even for some terms like 30 plus. Okay, why? Because it's the growth is exponential here. It's not logarithmic or additive, but it is exponential. Okay, so now let's move on our discussion to the class of P problems. So this P type of problems refer to problems where an algorithm would take a polynomial time. Okay, so you can see that to solve that problem, any problem, this type of class P problem would take polynomial time for solving that problem. So here, most of the applications we can solve in the time of big O of n of k, n power k, sorry. So for some constant k, and n is the size of the input. So here, this n plays a crucial role in determining the time. Okay. So now, for example, polynomial time, we can say that like O of 1 Okay, I'm sorry. So next one is we can go of O of n, O of n square, etc. So these are some of the polynomial time problem solving time with respect to big O notation. So these problems will be considered very easy to solve. Okay, and they do not generally have immense run times. In the sense, it can be solved in a very less time. Okay, such type of class C problem. So actually, if you go for any program verification, what is it, software like Pharmacy and all, you can always check for the complexity of problem. Here we have a problem to find if a given number is prime or not. So what happens here is this particular what is it piece of code, it loops until it finds until the square root of n. So it should be big O of square root of n. So, but what is the input size? Well, because as I told you in the previous slide, yeah, just a minute, this n plays a crucial role in this p type of problem. So here it depends upon the n value. So what is the square root of n? So the square root of n is nothing but we can represent that in terms of 2 log n. Okay, so which is 2 power k of zero point 0.5. So this is what or this is how we test for this particular problem. Okay, don't worry if you're not understanding the concept, but because this is just an example to show how P type of problems are computed, right? So anyway, you just know what is P type of problem. That's sufficient and more for your theory of computation. Why? Because these are all things related to your design and analysis of algorithms. So I think this is not required. We'll move on to the next slide, that is NP. So what is this NP? Say this NP here stands for non-deterministic polynomial problem. Okay. So it is not a non-polynomial. It is not that, but it stands for non-deterministic polynomial time. So what is this NP problem? So these are a little harder when compared with the previous one. So in terms of solving this NP problem, the runtime would not be polynomial. Okay, that is the difference between P and NP. Where P type of problems can be solved in polynomial time, whereas this NP problems cannot be solved in polynomial time. Okay, that is the runtime would not be polynomial here. So what is this? So what is the meaning for this NP? So NP means it is verifiable in the polynomial time. It is not solvable. There is a difference between solving and verifying, right? So for example, let's consider runtime something like O of n factorial. Okay, see, in factorial, the growth is not polynomial, but it will be much exponential, right? So, or much larger than factorial, something like that. So, this class of problems can be given a specific solution. That is, our answer is there, and checking the solution would have a polynomial runtime. So, that is what I told you. That is verifiable in polynomial time. Okay. So it has a solution, but for getting the solution, it won't have a polynomial time. It will have more time than a normal polynomial time problem is. But for checking whether the solution is correct or not, that is to verify that it requires polynomial time. So this is the meaning of this particular statement. Okay. An example for this is a common Sudoku game, which I think even in newspapers and some apps are there. So this Sudoku game is an Sudoku, right? Whatever you pronounce. It's a classic example for this NP problem. Okay, I repeat again, NP stands for non-deterministic polynomial time. It is not non-polynomial. Okay, you have to keep that in mind. Okay, so let's consider this Sudoku example. If you want to solve this entire puzzle, the algorithm would have to check a minimum of 3 by 3 matrix. Maybe 9 cells will be there, minimum I'm saying, right? Okay, so here what happens here, whether the numbers, we have to check whether the numbers are missing here or not. So once we find that something is missing, okay, we have to check whether we have to fill all those values, and we have to check whether no repetitions of digits from 0 to 9, that is in that 3 by 3 matrix are present. So this becomes complex. Why? Because the number of digits that are missing are inconsistent in each row and column. We cannot guess why. Because the top left matrix is will be having some 4 digits, while the top right will have some other missing numbers. So solving this problem would not have a polynomial runtime. It will take more than a polynomial time. Okay. So if you are feed with a puzzle, that is with solution, okay, the answer for that Sudoku what is it, problem is given to you. To verify whether that problem is correct or not, it requires polynomial time. That is the meaning for that. Okay. So for filling all those missing numbers in a Sudoku matrix is really tough. It will not be it cannot be done in a polynomial time. Whereas once the answer is given, we can check that in polynomial time. That is the meaning for this verifiable in polynomial time. Okay. So because it is much less complex to check if there are any repetitions in the rows and columns when compared with filling the values. I think filling the missing values will take more time when compared with that of checking whether it is correct or not. Okay. So the NP class problems uh, don't have a polynomial runtime. Okay, I'll repeat again. The NP class problems don't have a polynomial runtime to solve, but have a polynomial runtime to verify. Okay. So this is a very important statement that you have to keep in mind. So the concept is quite simple. It is difficult to solve the problem, but it is easy to check if the answer is given. Okay. So this is what with respect to the NP problems, that is non-deterministic polynomial time problems. So the example we have discussed now is the Sudoku game. Okay. So let's now move on to our discussion to automata, right? Because this subject is specific to theory of computation. So a problem is in NP, that is non-deterministic polynomial time, if and only if it is decidable by some non-deterministic Turing machine. So we should have a non-deterministic Turing machine. Okay. And how much time does it take? It takes a polynomial time here. Okay. So what is the meaning for that? That is the Turing machine, the non-deterministic Turing machine can verify. Okay, can verify. It is not that it can solve the problem. There's sorry. There's a difference between solving a problem and verifying the problem. Here we can decide. Do you understand? It can decide, not solve. Okay. So which can solve? The non-deterministic Turing machine can solve that, or sorry, can determine that it is a NP problem in polynomial time. So see, whatever we were discussing until I think maybe in your 4th unit, you might have discussed about Turing machines, and all those Turing machines were deterministic Turing machines. Okay, so actually an NDT, that is non-deterministic Turing machine, is equivalent to what is a deterministic Turing machine. Probably in your first unit or second unit, you might have proved that an NFA is equivalent to a DFA. Similarly, here also, a non-deterministic Turing machine is equivalent to a deterministic Turing machine. So this is what is given here. So we have, sorry, I have typed it out, I'm sorry. So we have converted NFA to DFA, DFA to NFA, etc., etc., etc. So we can also prove that deterministic and non-deterministic Turing machines are one and the same. So here the deterministic version of a non-deterministic Turing machine, okay, will run in exponential time. That is, it is the worst case, so it will take exponential time. Probably these terms and all you have to revisit with your what is it, earlier DAA classes. But don't worry, if you don't remember all those things, just keep in mind that the deterministic version of a poly time non-deterministic Turing machine will be in exponential time, right? So another example, I have given an example with respect to Sudoku game, but we have other examples also like graph theory. So this graph theory is a very interesting subject. I don't know, it was in the 7th semester earlier, but I think Anna University has moved it out of the 7th semester to an elective paper. It was a core paper one. but it is quite interesting and challenging paper. So this graph theory has some fascinating pair of NP problems. One is the shortest path algorithm. Probably this algorithm you might have studied in your DA as I told you, like the traveling salesman problem. So to find the shortest path between cities so that that person starts from a place and again reaches this hometown, visiting all the places exactly once, something like that. Okay. So this shortest path problem or algorithm comes under this NP problem. Okay. Next one is the longest path is NP complete. Maybe you might have not studied this longest path in DIA, but maybe if you take that elective in graph theory, you might undergo this algorithm. So this the longest part is NP complete. See, we are just discussing about NP problems only. We have not started our discussion on NP hard and NP complete problems. So we'll define that NP complete later. Okay, don't worry as of now. I'll just explain what is NP complete at a later part. Okay. So coming to the next example. So example number one for NP problem is shortest path. Second one is longest path is NP complete. Okay. I'll just give you the relationship between what is NP, NP complete, N and P, sorry, P and NP type of problems using a small diagram, Venn diagram. Okay, maybe at some point. Okay, I just draw it here. It's not a problem. We have initially the small. Sorry, I think this circle is not good. So I'll draw here. So initially a small set of problems comes under this polynomial sign, which we discussed at the starting of this PowerPoint presentation. So above this is a superset of these p-type problems, which we call it as the NP, that is non-deterministic polynomial sign problems, which we are discussing now. Okay, for p-type examples are problems which take n of 1 or sorry o of n, 1 or o of n, something like that. And for NP, I think the examples for Sudoku, graph theory problems like shortest path, longest path, Euler's tour, etc. and Hamiltonian tour, etc. Right? Okay. So Euler and Hamiltonian, etc. Okay. So this is the relationship between P and NP. But I told, or we were discussing about another class called as NP complete here. So what is this NP complete? There is another subset class of problem which we can call it as NP hard. Okay, I'll explain about NP hard and NP complete later. Okay, so we have a class of problems called as NP hard, and there is this NP complete. So this NP complete is something like an intersection of NP and the NP hard problem. Okay, so here we can say that this intersection part is there, no? Just a minute. Yeah. So this particular part, this green shader, I can call it as NP complete. Okay. So it is something like an intersection that occurs between this NP and NP hard type of problem. So this is a Venn diagram which represents the different class phases which in terms of P, NP, NP hard and NP complete. Okay. So I hope you just got an idea of what is NP complete. Probably if you want you can note down this Venn diagram, but because it is not present in the PPT, even if I share the PowerPoint presentation, I think these annotations will get deleted. I don't like keeping the annotations anymore. So I'll just give some time for you. You can take down this block diagram. Okay, so this part you can take down. Okay. So it should have a P. P is a subset of this NP, and yeah, NP hard has some common problems with that of NP type of problems, which we call it as NP complete problems. Okay. So this is a relationship between P, NP, NP hard, and NP complete. Okay, coming to the examples back, I think the time was enough for you to copy down this small Venn diagram. Okay, so coming to this example, like shortest path, longest path, and third one is an Euler's too. So actually, these two mathematicians, Euler and Hamilton, have given or have contributed more towards this graph theory. And graph theory finds its applications in all sort of computer science applications. Like computer networks for routing protocols, they use this graph theory, and they use it for what is it? Finding a path between two nodes, etc. Okay, so what is the difference between this Euler, what he said, and what this Hamilton said? Okay, see, a graph is nothing but we can say that it has got two tuples, B comma E. So a graph has got two tuples. So what is this V? V stands for vertices and E stands for edges. So a simple graph will be something like this. Okay, it is a directed graph because an arrow mark is there. So we have two vertices V1 and V2, and we have one edge, let me call it as V1. Okay, so this Euler, this mathematician, his all his theorems were based on these edges. Probably you can easily remember EE, Euler for edge, EE, right? So you can see that this is every vertex but cover every edge only one. So all his theorems are based on edges. Whereas this Hamilton, okay, he was talking about the vertices. Okay, all his problems were more oriented towards the vertices. So here, visit every vertex, no vertices can be repeated, and this is also another NP complete problem. This Hamilton tour is an example for NP complete. So longest path and Hamilton in for NP complete problems. Shortest path and Euler belongs to pure NP problem. Okay, pure NP problem. So I hope you understand what is NP complete. It is NP as well as mix of NP and NP hard. That is, it is a intersection of both. Okay. So we'll move on to, I think we'll skip this Hamiltonian side. Okay. And examples for NP problems or SAT problems, or which we call it as a satisfiable problem. Okay. So an example for that is the CNF, that is conjective or normal forms. Maybe in digital electronics or electronic devices and circuits, you might have studied about all these things. Gates, AND gate, OR gate, etc. So a simple CNF can be written something like this, and we want to find a solution for this, which is NP problem. Okay. So just a minute. I'm sorry, actually I was getting a call frequently and just added. Okay, fine. As I told you, this SAT problems or satisfiable problems are an example for NP problem. Okay, similarly we have two CNF, okay, I don't think I want to waste time here. Okay, these are some graph applications which you can see later. Okay, so this I think I have already explained to you by in the Venn diagram. P is a subset of NP. Probably if you remember, P was a small circle, and above that we had a very big circle which was NP. This was the Venn diagram which we discussed. So P type of problems is a subset of NP. Okay. So since it takes polynomial time to run the program, just run the program and get the solution. Okay. But NP is a subset of P. Okay. That is NP a subset of P? Can anyone tell me yes or no? You can unmute yourself and tell me. Is NP a subset of P? Say yes or no. One can unmute and tell me. Okay, so P is a subset of NP and not vice versa. That is the answer for that. And also no one knows that if P is equal to NP or not. We can't say any solutions for that. Probably there are a number of questions. If you go for this website, you can get it if you really want. Okay, uh, what are the things that are not in NP? Okay, two examples are there. One is undecidable problem and another one is tautology. Coming to this undecidable problems, I think we discussed the problem called as membership problem and another one is PCP. That is the post correspondence problem. So we had two lists and always the two lists will not match each other. We discussed one example with that also. So undecidable problems and tautology comes under this where it is not NP. Why? Because we cannot say that whether we can get the answer at polynomial time or NP time. Okay. Okay. Yeah. So before going to our discussion on the last two, so the last two is nothing but NP hard and NP complete. It is important to know about the concept of reduction or reducibility. Okay, reduction or reducibility. So here let's consider one problem Q. Okay, that can be reduced to another problem Q dash. Okay. So, or if you want, let's have this as A, problem A. Okay, I'm sorry. That can be reduced to another problem B. So, yes, we know that this B or Q dash can be solved in polynomial time. That is, B is a P class problem. Okay. So, A can be reduced or converted to B, and this reduction takes place in polynomial time. Okay, then we say that A is also P class. That is, A is reducible to B. That is, Q is reducible to Q dash in polynomial time. Okay, so let's consider a linear equation. Okay, that can be reducible to a quadratic equation. We have a linear equation reducible to a quadratic equation. Let the coefficient of the square term be taken as 0. So here this is an example for reducibility. So why did I introduce this concept? So this concept is very important to understand for the other two classes. One is NP hard and NP complete. Now let's move on our discussion to this NP hard problem. So a problem is classified as NP hard when an algorithm for solving it can be translated to solve any NP problem. Okay. So we can put it in other terms like the problem is at least as hard as any NP problem. Okay. Fine. So let's take for example, we want to find there are two lists L1 and L2, and we have to check if L1 is less than or equal to L2 in polynomial time P. You can see that word P here. So here this particular notation represents that L1 is reducible in polynomial time to L2. So here what is the meaning for this less than symbol? It means that the time taken to solve L1, okay, is less than, in the sense it is no worse than the polynomial factor taken to solve L2. That is, L1 takes less time. To be very in a straightforward manner, L2 takes more time than L1, or L1 takes less time than L2. Okay, now what do we infer from this? So a problem is said to be NP hard if every problem in NP can be polynomial time reduced to it. As I told you, the L1 is there. L is there, two different things. So here what we do is we reduce this L to L dash in polynomial time. Then we say that it is NP hard. That is only reduction occurs. Problem A is converted to problem B in polynomial time. We say that such problems are NP hard. Okay. That is reduction plays a major role here, and I have introduced what is reduction. So reduction is nothing but two problems, that is I have A and B. So if B is a P class problem, A can be reduced to B in the sense A becomes P type problem. Okay. So this is this type of problems we call it as NP hard. Okay. Then what is NP complete? We discussed about NP hard. Now what is NP complete problem? So, NP complete is to be both NP and NP hard. Probably in the Venn diagram, we had something like this. So, we had a NP problem. Okay, in between that, we had a P here. Okay, and we had another, what is it, NP hard. Let me put only H here. So this intersection between this NP and NP hard, we call it as NP complete. Okay, so it needs to be in NP, and it is also, and it should be in NP hard also. So this NP complete problems are problems that live in both the NP and NP hard classes. So what is the meaning for this? This means that the NP-complete problems can be verified in polynomial time, and that any NP problem can be reduced to this problem in polynomial time. So both are satisfied, then we say that it is NP-complete. So this reducibility is a transitive relation. Okay. So transitive relation in the sense, if we know a single problem is NP complete, then we are asked to prove that it is NP complete in the sense it will be either NP or NP hard. Okay, assume a problem is NP complete. All NP problems are reducible to this problem. So let's have another problem P dash. If we show that P is reducible to P dash, then all transitivity of all these NP problems are reducible to the P dash. Okay. So coming to this NP complete, particularly with respect to this TOC, we'll have an example. Given any Boolean formula, some Boolean expression using gates, etc., is there some assignment of values to the variable so that the formula has a true value? Okay, this is NP complete. So I think true value means it is tautology. Am I correct? If I'm not wrong, I'm not so good in digital electronics and all. So if we substitute some zeros and one something like that, the answer should be like all the values should be true. Okay, this is the meaning for. I'm sorry. This is an example for NP completeness. Okay. So as far as NP completeness is concerned, what is it? The running case may be O of n for some constant. Sorry, O of n power c for some constant c. Okay. So this is all about NP complete. Okay. So I think we'll stop this class, and I'll wait for some more time for you to get your doubts cleared if you have. Do you have any doubt? You can ask now regarding post correspondence problem or NP complete and NP hard problem. If you have any doubt, probably you can ask now. Yeah. Okay. Since no one is asking any doubt even in the chat window, okay, I assume that you have understood the concept that we discussed here. So once again, let me have a fast rewind of what we have discussed in the fifth unit. So fifth unit is somewhat pure theory-oriented thing. So initially we started our discussion on undecidability. So we started our discussion with RE languages, that is recursively enumerable languages. So it is a type 0 language, and these RE languages can be accepted or recognized by a Turing machine. So RE languages means the Turing machine will enter into the final state for the strings of languages that it accepts, or it may reject and it will go to the acceptance state. Okay, so it means that the strings are not part of the language. So here the Turing machine can loop forever for the strings which are not part of the language. That is the main thing of RE languages. Okay, so the machine will not halt, but it will enter to the final state. See, I have explained you clearly the difference between entering into a final state and the machine coming to a halt. And there is another class of language called as recursive language. So recursively enumerable means the machine will not halt. So this recursive language is a subset of this recursively enumerable language. So R is a subset of RE. So here the Turing machine will decide it will go to the final state, and also if the thing is not part of a language, it will reject that and it will move to the final state, and also it will always halt. That is, for a recursive language, the Turing machine will halt. Whereas for a recursively enumerable language, if it is not accepted, the machine will not halt. Okay. So these are the two important languages with respect to Turing machines on decidability. Okay. So there are some problems which are undecidable. One example is a halting problem. We discussed about Turing machine which will reject and then will not halt. That is undecidable problem. Okay, that is a Turing machine will not halt here. And of course, there are some theorems which are not in your syllabus. Actually, there is a theorem called as Rice theorem, which talks about the undecidability of a Turing machine. In the sense, the Turing machine will not halt if it is not, if the thing is not a part of the language. Okay. So coming to the next discussion, we discussed about a very important problem called the post correspondence problem. And if you look at the any Anna University question paper, okay. Yeah, someone has sent a message. What is it, sir? Screen isn't visible. Yeah, I'm not sharing anything. I'm just explaining. Okay. So I'm just recollecting what we have discussed in the past classes. So because we have come to the end of this 15 minutes. So we started our discussion with R and RE languages. So R language means the machine will halt. RE language means the machine will not halt. And we discussed about undecidability. So undecidability in the sense that Turing machine will not halt. So that is a Turing machine is undecidable. Okay. And coming to the next example, we discussed a few examples, and the most important example is the post correspondence problem. Okay. So post correspondence problem, as we discussed, two lists. One is list A and list B. So we discussed few examples. I think I have shared the PowerPoint presentation to you through that. I think you might have got that. So this post correspondence problem comes under the concept of undecidability. Why? Because not always we can match those two strings. Okay. And one example we discussed that there is no solution for that. If you take any combination from the list, we were not able to find any solution. And we moved our discussion to another thing called as modified post correspondence problem, also called as MPCP. Okay. So this MPCP actually, what is it? It took the first value, that is the first sequence present in both the list, and it further proceeded. Whereas PCP was not having that particular restriction. So we discussed two examples of PCP with one with respect to the context tree, grammar context tree, and one with respect to the Turing machine. So this is what we are discussing for the past four classes, and today we discussed about P, NP, NP hard, and NP complete. problem. So we had a nice discussion about what is class P problem, which means that problems can be solved in polynomial time, and NP stands for non-deterministic polynomial time problems. So here this non-deterministic polynomial time problems refer to problems which cannot be solved in polynomial time but can be checked or verified in polynomial time. That is, we can check the answer whether the answers are correct or not in polynomial time. So examples, so I think we discussed some 5 examples, not 5, actually 6 examples. Yeah, 5 or 6. Yeah, 5. One is the Sudoku, another one is the shortest path, longest path, Euler's walk, and the Hamiltonian walk, right? So these are the 5 examples we discussed under NP, that is non-deterministic polynomial time problem. And then we discussed about another class of problems which we call it as NP hard and NP complete. So what is this NP hard? NP hard problems or problems like what is it? We can reduce one sort of problem into another, problem A into problem B, and an intersection of this NP and NP hard problems, we call it as NP complete problem. So what is this NP complete problems? We cannot resolve the problem, but what we can do is we can demonstrate that certain problems are NP problems, right? Okay. So I think it's time up. So I'll wind up the class. So if you're having any doubt, you can stay here and ask me. Otherwise, I think with Gayatri ma'am's permission, if she permits, you can take off. So thank you all for listening to my class. I think this is the last class of Unit 5. Okay. So we have discussed about all the concepts that are present in the 5th unit. And I reiterate that the post correspondence problem is one important thing, one important problem in with respect to your Anna University examination. So they'll surely ask one question from that. So concentrate more on that. It does not mean that you should not concentrate on others. Others also you have to study, but this is a problem where you have to give much attention. Okay. Thank you all. Gayatri ma'am. Yeah, I think ma'am has left. Okay. Thank you all. Have a nice time. Bye.
Thank you, Krishna sir.